Hello, good morning to all. We will start the webinar in 1 minute. We will wait others to join, like give a few more minutes for others to join, and we'll start. Okay, it is. I think we can start. Welcome to the webinar series of ASE61850 Test Set. And you can see previous webinars from our website. You'll be able to register and view them whenever you like. So today's webinar is about interoperability workshop that we have participated in 2024 September. And today we will talk about the takeaways and ASE experiences during this interoperability workshop. I'm Sterling Jose, and I am handling the technical activities at Applied Systems Engineering. I am doing the product management of ASE61850 Test Set and BNET products at ASE. So today's agenda is to cover ASE61850 suite and BNET product introduction to you. If you are not familiar with our test set product, you will get an idea of what it is and what it can do with respect to the 61850 capabilities. And we will also talk about ASE's interoperability participation history. Then we will cover what are the highlights in interoperability 2024, what exactly was done newly compared to the previous IOPS. We will talk about that. And we will also describe how ASE participated in the workshop and what were the products used in the workshop and the roles of each products in the workshop. We will also briefly cover the functional test case definition mechanism and a concept called BAP. This was introduced in this IOP, and we will cover this briefly. And we will also see the participation metrics of ASE products across different bays and slots. So we will cover that briefly. And finally, we will have a demonstration. It will be a brief demonstration of line bay test slot 1. And in this, we had participated as a pay controller unit and a circuit breaker emulator. We will see the brief demo of this capability. Let us start with the introduction to the Applied Systems Engineering. If you are not familiar with Applied Systems Engineering, ASE was founded in 1988 and Calcitech was founded in 1998. Later in 2014, 2015 timeframe, Calcitech acquired ASE, and ASE originally had test set products and protocol gateways, and Calcitech also had several of these communication products, and by merging these two entities, we now have a lot of capabilities in the protocol, and we are basically providing a lot of communication solutions to the industry. Okay, coming to the ASE61850 suite of products, we have under this brand we have SCL Manager. It's a full-fledged IEC61850 SCT. It can do substation configuration and substation specification. So you can use this in the project planning phase by importing all the ICD files, CID files, and create the full engineering of the substation. We also have a scalable server. It is called IED Smart. It can be used for the large-scale simulation of the substation. It also has the scripting capability so that you can simulate advanced scenarios. If you want to do some kind of a basic protection, you can create a logic in the server product and do that. We also have the client capability. It is called ASE61850 Test Set. Originally, this was built as a client tool, but later we integrated the server capabilities and monitoring mode capabilities into the test set. So now we have kind of two products supporting the server. One is IED Smart, which is a scalable solution that supports scripting, and the test set also supports server capability. So with test set, you will be able to do client, server, and monitoring mode. Monitoring mode is a special mode where you listen to the traffic, mainly connecting to the mirror port of the switch in the substation, and you can essentially view everything from that mode. So that will give you a lot of capabilities from monitoring, from troubleshooting perspective. And recently we launched a hardware product called the BNET. It will be an accessory to ASE61850 Test Set. This hardware works with the test set to provide you the sample to value capability. And so if you want to troubleshoot the process bus, then you can kind of use this hardware and connect to the station bus and process bus and troubleshoot everything from there. And the high processing capability of the BNET will allow you to do a lot of advanced troubleshooting on process bus network. It can identify the missing of packets in the network or delayed packets in the network. It can find out the drastic RMS changes and angle changes in the currents and voltages. So it can scan the sample value packets in the network. So a lot of capabilities with respect to the process bus are available in BNET hardware. So this is how BNET works in a substation. It has got 4 Ethernet ports. 2 of them are SFP ports, which can be either a Ethernet port or a fiber optic port. By default, BNET is shipped with the fiber optic port, and Ethernet ports can be used primarily if your network is Ethernet based. You can use these left ports, and if you have fiber optic connections, then you can use the right side port to utilize that. So with BNET, test set can do all the station bus and process bus simulation, testing, and monitoring. Let us get to the topic of interoperability. So initially, we will talk about our participation experience in interoperability workshops. We started from 2015 and participated in all the IOPS from that point. Initially, we were focusing on participating with SCL Manager during this IOPS. SCL Manager was our SCT tool. It helped to kind of create the substation configuration. In the initial stages, we used to kind of split the entire IOP into 2 areas, like high voltage and low voltage areas. And SCL Manager used to configure one of those substations to import all the configurations, ICD files into the project and create the signal mapping and do the system engineering. We have interoperated our SCT tool with almost all the vendors in the industry. You can see the bigger list here. We have kind of tested our tool with several of these vendors, and over the period of time, SCL Manager evolved as a full-fledged SCT supporting edition 1, edition 2, and edition 2.1. So you can see the progress from this point. And from 2021-2022, we also started SCL IOP process. That means SCL IOP was introduced to ensure that the ICD creation part is done upfront, and the basic validation of the ICD files are done much earlier. In the previous IOPS, this used to be done during the interoperability workshop itself. That used to consume a lot of time. A lot of initial stages or initial days will be spent on validating the ICD files and verifying some of the basic functions. So that used to cause some delays in the process. But from 2021, the process was changed a little bit so that the ICD file validations would be done much earlier, and the face-to-face IOP will not have any delays to start the actual testing. So that is the history of ASE's IOP participation, and in 2021 also ASE61850 Test Set was participated as a bay controller unit in functional testing. So from that point, we started participating with the BC capability as well. In addition to SCD, our tools started to participate in the functional testing area. So let us get into 2024 interoperability workshop highlights. Again, 2023-2024, it was similar to what we done in 2021-2022 IOPS. So that means we had a SCL IOP earlier, and then later the actual face-to-face IOP was focusing on the functional testing part. SCL IOP, we participated using our SCT, and we had several substation exchange description use cases. That means multiple SCTs were used to create the configuration, and we exchanged that configuration and tried to find out whether there is any interoperability issues from that perspective. So there were 4 SCTs participated during that trials, and SCL Manager was one of them. And in face-to-face IOP, main focus was on the functional testing. There were some side streams for security testing and other things, but mainly the IOP fully focused on the functional testing aspects. So that means the actual use case of a protection scenario would be created, and it will be tested against the vendor devices. And the basic application profile concept was introduced in this IOP so that there are multiple areas that can be tested at the same time. So earlier, there will be a high voltage substation area and a low voltage substation area, and if there is any delays in the process of testing on any of these devices, then the entire test would be delayed. So new concept of multiple bay testing avoided that problem up to a certain extent. There was still some confusions on using this new approach, but overall it helped to streamline the preparation and testing process. So that means when one bay testing happens, then other devices in other bays can be prepared and kept ready for the future tests. So this avoided the need for kind of waiting for all the devices to come up. So everybody spent time on preparing their devices when some other test was going on, and then later the slot is available, then everybody could start the testing almost immediately. So that was one major change in this IOP compared to the previous IOPs. In the same fashion, we had multiple SCTs configuring different bays. So that means whoever has SCT could participate as a system configuration tool and test the interoperability with the vendor ICD files. So there were 4 SCTs in total configuring multiple bays. And we also had a network configuration which allowed different vendors to participate from a networking standpoint. So that means we had different bays, and each bay would be covered by one network vendor. So that means it allowed multiple. It actually allowed different network providers or network vendors to test with all these individual vendor devices, right? It gave a lot of combinations. So a lot of functionalities were tested from that perspective. Getting into the functional test planning, so we had multiple such BAPs or basic application profiles defined and documented. This was a very elaborated documentation in this IOP compared to the previous IOP. So earlier we used to have we used to draw on a board and define the signal exchanges, and that was it. but that caused some delays in the process, and this time a lot of time was spent by preparing these BAPs, and all the details were captured in these individual documents specific to the use case. That means breaker failure function. It had a specific document, interlocking and synchro check. It had a separate document. That means it was very clear on what to do on a specific test, on which all devices will be involved, how the signal exchanges will be done. All these things were laid out in a very clear fashion, and there was no confusion while configuring or engineering the system. So this is an example of line bay protection scheme. Next, we'll talk about the logical architecture of BAP. So generally, there was a convention followed in each of these BAPs, that there will be a breaker interface simulating a circuit breaker, and there will be a switch controller which will be kind of accepting the control to the circuit breaker, and based on the interlocking, the bay controller will allow the circuit breaking function. And also we had switching functions like line side disconnector interface and bus side disconnector interface. So these were kind of standard approach followed in most of these BAPs. And we also had the merging unit collecting the voltage and currents from the system. So this kind of general topology helped to prepare all these devices. So that means most of the base will have merging units collecting the information from the system, passing it to the protection devices, and bay controller allowing the control to the system, providing synchro check and interlocking functions for the HMI user to control the circuit. So all these functionalities were defined, and reports, goose, and sampled values were configured to exchange the signals across the system. So this standard approach helped all the BAPs to function in a streamlined fashion. Now we will talk about what ASE contributed into the interoperability workshop. There were several use cases that were covered as part of the SCL IOP, which was done in 2023. And primarily, this was focusing on SCD, or System Exchange Description, or Substation Exchange Description. So this allowed the SCL Manager to test the interoperabilities with other SCT vendors in the market. And there were 4 SCTs participated in SCL IOP, and SCL Manager could successfully exchange files or configurations with all the other 3 SCTs. Then in the face-to-face IOP, SCL Manager again was used to engineer 3 bays with multifunctional BAP tests. That means a lot of vendor devices were used in these 3 bays, and by using SCL Manager in all 3 configurations, it allowed to test the interoperability of SCL Manager with other IEDs, or intelligent electronic devices. It could be a HMI, it could be a merging unit, or protection interface unit, or bay controller unit, or protection relays. So we had 3 such configurations created using SCL Manager. Then ASE61850 Test Set participated in functional testing as a bay controller unit. It participated with the logic capabilities. So this was a newly introduced feature in the previous IOP. We had the basic functionality at that time, and we could participate as a PCU with the minimal capabilities. But those functionalities were extended and made available in the standard release right now. So anybody who has the test set will be able to utilize this logic capability in the test set. So bay controller unit was one functionality, and we also simulated the circuit breaker. So that means if the protection interface unit need the circuit breaker status from the system, our test set would provide that by looking at the breaker status. And HMI functionality was also tested in several of these BAP tests. That means across the system test set, our test set will be configured like a client or HMI, and we would track the transactions between all the devices using reports and goes, so we can see the sequence of events in the point list and other interfaces in the test set. So these were the three roles, like B controller unit role and circuit breaker emulator and HMI. So all these functions were tested successfully. So we'll briefly talk about the pre-event planning and organizing. There were four separate networks created as part of the interoperability workshop, and this allowed multiple BAPs to run concurrently. Even though there were more than four bay configurations at a time, it allowed to like engineer or create a network for four separate LANs. And each LAN used to be assigned with one specific BAP at a specific point in time. So that means when one LAN is under testing, then the next other LANs would be preparing for the test. So this allowed all the vendors participating in different areas, preparing their network for the configuration, and kind of finally run the test when the slot comes. So there was an individual SCD for each LAN or slot. So this allowed all the BAPs to run concurrently if required. So that means we could run four BAPs concurrently if required. But to get the full attention at any point of time, it was the slot was created in such a way that there will be only one BAP run at a time. But the preparation could be done separately for each of these LANs. And finally, multiple vendors and participating devices with different roles allotted to each slot. So that way, everything was clearly mentioned. And this is how the participation metrics used to look like. There will be a vendor column, then model, device ID, and there will be several status indicating the capabilities of these devices. So you can see that ASE Calcitech participated with our test set as a BCU, as a circuit breaker emulator, as a client HMI, and finally as a process bus monitoring device. So we marked our capabilities, like we indicated that functional testing will be done with all these products, and BNET allowed the sniffing capability to look at the process bus and station bus traffic. And coming to the roles of ASE devices in different testing areas, you can see that in some of the tests, our devices was participated as a circuit breaker emulator, and client in some other areas it was participating as a BCU. So we kind of marked all the roles in these tests, and based on that role, the SCD configuring engineer will be kind of assigning these devices, assigning these ICD files into the system, and configure accordingly. This is the full list of tests that we ran during the interoperability session. So you can see that which SCT was used in the configuration process. So ASE, here you can see that ASE was used in test 3. And if you go to the other tests, you can see that different SCTs were used in each of these processes. And coming to the devices, you can see that the highlighted device was participated. Like here, ASE, we participated as a circuit breaker emulator. In the first test, it was configured as a B controller unit and a circuit breaker emulator. In other tests, it was configured like a client. So in all these tests, we participated with the different roles and capabilities. And here you can see that we participated as a BCU and a circuit breaker emulator and a client here. So we switched roles in different scenarios. ASE test set being a flexible IED, it can act either as a client or as a by controller unit or a server or a monitoring device. So we could kind of do all these tests without any issues. Coming to ASE61850 Test Set demonstration, today we can see the line-based test capability. So here we will use the SCD file generated for line-based test 1, and it performed several of these capabilities, but for the demonstration purpose, we don't have the other IEDs right now. So we will be simulating some of the other IEDs here during the demo. So we can see how the test set can load the configuration and how the project creation is done. At a high level, the project is already created, but we can walk through the individual configuration so that you are familiar with the process. And finally, we can see the use of simulation and logic. After the demonstration, we will also talk about the sample project. So sample project is basically a way to get started with the test set. Once you install the software, you have the client project and server project, and we have used one of the interoperability line-based test for this project. So that means whatever we are going to see in this webinar, a version of that project is already created as part of the latest 61850 test set. You may download it from our website, and you can kind of familiarize with the entire process. So you can load you may load the client using the sample client project. You will be able to load the server capabilities, multiple IEDs using the sample server project, and we have already installed this ICD file or a SCD file, that line-based test file, as part of the installation. So you will be able to easily open this file and run the simulation. If you run the simulation in server mode, you will be utilizing 2 of these logic files. I will go through that briefly. So it has some basic simulation already pre-configured, so you'll be able to run them with these files as part of the project. Okay, let us get into the demonstration part. I'll briefly switch the screen. So initially we will start with the SCL Manager. We will show you the configuration file. So let me start sharing my screen. Okay. So SCL Manager is a standard SCT, and we can load the configuration already configured SCD files into the SCL Manager, or you may create a fresh configuration using SCL Manager. I'll create a sample project. To load this configuration, so I'll use the SCD wizard to import the configuration into the system. So let me import this file. So initially it will import the single line diagram part of it and then list down all the devices. So this file was taken from the Interoperability Workshop line-based test. It will analyze the configuration and will start importing the file. It will show you the progress of the import process here. And it will also indicate the version of IEDs used in all these configuration. So here you can see that the transformer PIU was using a edition 2.1 file, and LPIU is using a edition 2 file. So this will allow you to kind of find out how each of these configuration looks like. And if you double click, you will be able to see the detailed configuration of all these devices. Irrespective of the vendor, our user interface remain the same. So you'll be able to see the communication section, logical nodes, data sets, goose, everything from a device here. You'll be able to see the access points available under each of these devices. And you can also browse through all the logical devices using this interfaces. Other useful information in the SCL Manager is the signal metrics. So you'll be able to find out how the signal mapping between these IEDs happened. In this configuration, so you can see that this is on the left side, you'll see the source of the signal. Here you can see that it's transformer TFPIU, and it is sending the circuit breaker status, and then the information is going to the HMI and monitoring device and other devices across the system, right? And if you scroll, you'll be able to find out how the signal matrix is fully aligned. So this helps you to kind of find out how the signal configuration is done across the system. So yeah, this helps to filter out the goose signals. So if you are only interested in goose, you can select the goose filter here. Or if you're interested in reports, you can check that. And you can also check the sampled values specifically. You will also be able to filter individual devices. If you are interested to see a specific transaction from, say, TFPIU, then you may deselect all and select the TFPIU and then go with the other devices. So based on that, you'll be able to kind of filter all the individual transactions. So you can trace the source of the signal and also the destination using this method. We also have the network addressing capability. So that means you can see the substation configuration here, like with what are the sub networks available in a substation. And you can also see the IEDs configured under this subnetwork. In this case, we only have one subnetwork, but in other substations, you might see multiple subnetworks for station bus and process bus. And you can see the IED name, manufacturer name, access points. In some cases, you will see multiple access points. You can see here, or more than one access points in some other cases. And you'll be able to see how the access points are assigned to the subnetwork. Here you can see that some of the access points are not connected to any subnetwork in this case. And you'll be able to see the IP address, subnet and gateway, and also the schema version. If you go further, you'll be able to see the goose communication information. Like if you are interested in the multicast addressing, then you can look at this MAC address column and find out the details here, and other information like app ID or VLAN ID can be found in these columns. You'll be able to change the configuration here. In this case, we are only browsing through the file, but in actual scenario, you'll be able to make changes and save. You can also see the sampled value configuration here. There is only one merging unit publishing the samples in this scenario. And you can also see the reports that are configured or available in the system. Some of the reports are not used, but there are many configured. Here you can see that there are some buffered reports configured for the HMI's use. This will give you a complete list of the goes, reports, and sample values. And you'll be able to see the addressing information here. So these interfaces will give you kind of pretty good idea on how the system is configured and how it is running. So going with the server simulation, the main part of the interoperability participation was the server. We participated as a big controller unit, and we also participated as a circuit breaker emulator in several of these use cases. So I have a already created configuration for the server, so I'll open that and demonstrate that capability. So this project is created for the server. I'll load the server and show you how it looks like. In the actual interoperability, we had kind of included only the big controller unit here, but since we don't have those other devices for this demo, we are also simulating those. So using the capability of test set, you will be able to simulate multiple devices. So you can see that in this scenario, we are simulating a big controller unit, then PAU, then protection unit, and other capabilities. So you can see that all these devices can be assigned with a specific IP address. In this case, I have assigned alias IPs to the computer. So you'll be able to kind of see all these devices here. These are the actual ICD files or the configuration as per the substation configuration. And if you look at, if you click on any one of the device, you will see the manufacturer or other information here. And you can see that this is a PAU supplied by Schweizer, and this is a protection unit supplied by Siemens, and this is a circuit breaker emulator. Okay. This way you can kind of simulate multiple devices if you are specifically interested to see the transactions, or if you want to test one device, you can simulate the rest of the devices in test set and create that environment for the test device. And some of these configurations are kind of created earlier. This is one important tag. It will trigger the simulation across the system. That's why it's called circuit breaker trigger indication 1. Ghost messages are mapped across these devices. You can see that all these ghost messages are already live in the system. We'll primarily focus on the ghosts in this demo. So you can see that the current state change, and also if you click on one of the ghost entry, you can see the data point values changing. This is the initial state of the system, and if we go to the point list and trigger any change here, for example, I'm going to change this to true. So you can see that based on the logic that is configured in each of these devices, it triggered a series of transactions based on the simulations configured. If you go to the goose tab, you'll be able to see the new goose signals that arrived. You can see that the circuit breaker status changed to close based on the trigger received. So the state change number also can be seen here. So all these are happening based on the logic that are configured in these devices. So I'll briefly talk about how the logic configuration is done, and we can go from there. So for that, I will open the user manual of test set. And if you browse to the initial part of the document, you will be able to see the logic configuration. So you can search for the logic. These are the logic operations supported in test set. It's generally using a CSV file format. There is a format that you need to follow, and you need to keep the logic files in specific location. Right now, the user interface for the logic configuration is not available in the test set because it is meant for the advanced users. At a later point of time, based on the interest from the users, we might add the logic configuration capability in the user interface. But at this point, you'll have to go with this file format. There are certain logic types available. One is the set. This is the basic function uh, that can be used to set a value in the system or in the server, and to set the value you can specify the conditions. And so that means you will be able to kind of define one or more conditions to specify a value for a 61850 variable. And you can also define logic for the control. So that means if you want to control, if you're acting like a server, and if you're receiving a control from a HMI, then you can define how the control should be handled. In some cases, you want to pass the control directly to the status value that is supported by default. But if you are interested to um, apply certain logic before triggering the status value changes or simulation, then you can do that. Basically, the interlock check or synchro check or other capabilities can be defined using this logic type. So these are the two primary logic types. We also have a capability to introduce a delay in the action. So that means if you are interested to kind of set a delay, instead of doing it instantaneously, you may introduce a delay and do the same action. So this will allow you to assess the situation or condition multiple times. So that means initially when the condition is met, it will trigger the activation, or it will arm the action, but it will actually perform the action only after the delay. So this will allow you to kind of control the simulation in a defined manner. For example, if you are uh, tripping a circuit, for example, if you are acting like a protection relay, you want to trip the breaker, but you also want to reset the trip status, right? So after some time or after a few milliseconds, you want to kind of go back to a different state. So those kind of advanced simulations can be performed this delay parameter. And then you have a target element. Target element is nothing but the value that you will be changing in case of a situation. So that means you will be able to define the full path of a 61850 variable here and specify a value for that. So for Boolean values, you'll be able to set 0, 1, and for double position, you'll have to set 0, 1, 2, 3. In future, we will provide you the user interface to set these values, but till that point, you'll have to use these values. And you also have the logic operators. That means if you want to evaluate multiple conditions while performing an action, you can use these operators. You may use AND operation or operation. And in some cases, you want to simply copy the value from one 61850 variable to other. So in such cases, you can use the copy operation. Copy operation will only have one source and destination. You can also specify the number of conditions, especially for the and or conditions. If you want to evaluate multiple such conditions, you can specify that here. And there is a way to kind of identify the nth condition. You can specify a tag and also specify a comparator. So there are several such kind of options that allows you to control the simulation sequence. Another thing that I want to highlight is the sample project. You may search for the sample and you will see how to access the sample project in the test set. The same line-based simulation is converted as a sample project, and you will be able to see that in the specified path. So these two will allow you to understand how the logic functionality is implemented and how you can kind of build a simple or advanced logics using test set. Going back to our actual files, so we saw the simulation. We saw that if you trigger one value, you are seeing multiple of these simulations, right? So let us see how those simulations are triggered. So this value, you can see that this was the trigger of the value, and here you can see that this was in LPAU, right? Uh, and if you see the LPAU, and you can go to the subscribed goose to understand how the inputs of these goose will work. You can see that in BCU, the LPAU messages are used. So interlocking function is primarily coming from the LPAU, so that is used as a trigger here, right? And if you expand the LPAU, you will be able to see all the goose messages that are going out from there. And if you go to the data set, you will be able to see all the tags that are assigned for this purpose. These tags are transferred to the BCU, and it is performing certain interlocking conditions based on the remote tags. Now let us look at the BCU logic. This file looks complex, but actually it is kind of straightforward. Since we have already gone through the documentation part, it allows you to kind of go through the file easily. You need to define, the first line is defining the format of the file, and second line is commented out, but it is actually a control logic. It is commented using this hash symbol. And you can see that the actual logic that is defining the control is the line number 4. So line number 4, what it does is, it is the logic type is control, and you can see that the it is looking for the operate value, CTL val 0, and the condition it is looking for is the enable operand. So unless the enable operand is 1 or true, it will not allow the control value 0. So that means it will not allow to open the breaker, open the switch position, unless the enable operand is true. Basically, it's a kind of interlocking condition that blocks the control. Similarly, to close the breaker, you need to have the enable close parameter 1. So this way you are basically defining the way the controls are handled if the HMI is issuing a control. Similarly, you have some simulation functions to determine whether the enable operand should be true or not. So here what it does is, so here you can see that enable operand is here, and it is set to true when two conditions are met. So first condition is that the PAU, line PAU should provide the switch position or a disconnector status as 2, which is the close position. So this means you should have this status as closed, and you should also have the other disconnector status as closed. So that means unless both the disconnectors are closed, then only the enable operand will be allowed. In the same way, this is the reverse condition. So here it is checking for the other status, like when it should reset the enable operand. So if any one of the disconnector is not in closed state, that means enable operand will be disabled. Similarly, enable close is also controlled. So this is a kind of basic interlocking function defined here using these 4 instructions. You also have the circuit breaker update logic. So that means if the circuit breaker status from the protection device it's the status from the PAU, if it is, it is basically copying the circuit breaker status from the LPAU to its own circuit breaker status. That means from a BCU's perspective, it is providing the status to the HMI. So it will have a CSWI, and the position of that circuit breaker will be indicated by using the status from the line PAU. So this gives you multiple options here. Like you can either copy the value from a source to destination. This value could be coming from a remote goose, and you can copy the value to a destination. So destination is mostly the value that you are simulating locally. So that means if you are simulating a BCU, you will be kind of setting the value in the BCU here. And the conditions, you will mostly refer to the conditions that you get through Goose. So on the right side, you will mostly see the values that are available in the remote devices. That's how generally it looks like. So all the tags on the right side, basically you will find it under the subscribed Goose. And all the tags on the left side, you will basically find in the local data model of the system. Okay, that's how the protection logic is configured. In the same way, the circuit breaker simulation is configured. You can see that there are several goals that are subscribed, and based on that, it is simulating the circuit breaker or switch position. To view that, I will open the TE, which is the circuit breaker emulator, and here we are simply mirroring the status from based on the GGAO. So if a GGAO status is triggered, it will set the status based on that. So that means it will look at the status from a few tags in the remote, and based on that, it will set the local tag. So you can see that the XCBR status is set here. It's setting the GGAO status based on the remote value. These are simpler simulation compared to the BCU. So here it is basically handling the interlocking function. You will also be able to simulate the analog values using the same logic capability. So since we have covered the basic logic functions specific to the interoperability sessions, I can help you navigate to some of the other logics that are already packed along with the test set. So I was telling you earlier about the sample project. Yeah, under the sample project, if you browse, you'll be able to see. Okay, I'll bring the screen here. So this is how it will look like when you install the test set. You will have the sample project under this path, under the program data, applied systems engineering, ASE test set. You will have this sample project. You can open this project and easily familiarize with the method that is used in this line protection. And by opening the LPAU logic and PU logic, you will be able to easily understand the configurations. So here, some of the protection scenarios are also configured. Here, it will detect the overcurrent condition and trigger the PTOC. Here, it will detect the overvoltage condition and trigger PTOV. So to trigger these conditions, you will have to simulate the MMXU values. So if you manually simulate the MMXU values like current, phase A current here, you will be able to trigger the overcurrent PTOC status or PTOC trip. And based on the PTOC and PTOV, it will do the PTRC trip conditioning, and you can also kind of simulate the breaker. You can also reset the MMXU status based on the breaker status. That means if the breaker is open, you will not see any current in the line, right? So you can simulate those conditions. So this will give you a kind of better idea of the capabilities of logic. If you are installing the test set and if you are interested in performing this advanced logic, I would suggest you to go through this sample project and sample logic files to understand the capabilities. I think we have covered all the points. Yeah, I think we have gone through all the sample project. We have also discussed the test set demo and also went through all the scenarios that we covered during the interoperability. Looks like we are done with the presentation part of it. Now let us go through the questions. Okay, one question I see is that how the performance of test set. Okay, performance of the logic function is pretty instantaneous. We are looking at the network and based on the trigger from the network, it will simply import the values into the system and trigger the logic. So there is no periodic execution happening based on the events. All the logic executions are triggered based on the event. And so the test set will look at where the events are events to be used, and based on these events it will trigger the logic conditions. So that's how it is done. So the performance is pretty in millisecond, it will happen within a millisecond or around that time. So that's the logic. The next question is will it be possible to configure multiple IEDs? So as I shown in the demonstration, you will be able to kind of simulate multiple IEDs in the configuration. Here you can see that in this configuration we have 4 IEDs simulated. You'll be able to create an environment for the test device and simulate larger number of devices here. In the next version of test set, we are planning to offer verify IED capability or verify SCD capabilities. So you will be able to kind of simulate and verify the configuration of the actual devices against the SCD file. So that will be a good feature for you to look at. The next question I have is how the BNET was used in the IOP. Okay, to talk about the BNET participation, we did not actively participated using the BNET. It was only acting like a sniffing tool to monitor the currents and voltages. So what we did is we listened to the traffic and displayed the RMS values and also detected the delays in the network. So we could kind of internally demonstrate, or to the audience, we could demonstrate how BNET can find out the traffic in the network by scanning the sampled value streams, and also kind of show the delays in the network. It was not significant, but we could demonstrate those capabilities. I see these are the main questions I see. So I think we are almost running out of time. It's so remaining questions I am seeing some other questions as well, but because of the lack of time, I will respond to these questions offline. I will reach out to individual people who have raised the question, and I will answer them separately. Okay. Thanks everyone for attending and taking time for familiarizing with our IOP experience and tools capabilities that allowed us to participate in the IOP. Thanks a lot.